Okay, great. All right. Hello. Welcome to today's installment of the Corundum Developer Meeting. Today it's live from the lab at UMD. All right. So let's go ahead and get into what we have for today. Assuming my slides are cooperating here. Okay. Right. So we got announcements and status updates. Pretty straightforward announcements. The next developer meeting will be hopefully as scheduled October 1st, 9 a.m. The next Switch meeting, I guess, is going to be TBD. I'm waiting to hear back from Carlos in terms of what his schedule is looking like. Carlos, do we have anything to say about that or still TBD at this point?
Yeah, I think maybe we're gonna skip next week. Maybe we can do on to the next one. I can
Okay.
send a message
Yeah,
in the
well,
near future.
actually, so I think the next couple of weeks are going to be super busy for me. So I don't know if I'll be able to. I mean, I can certainly, hand the meeting over to you, but
Mhm.
I won't be able to put aside a whole block over the next couple of weeks here. It's the next 2 weeks are, when we're doing stuff in the lab here, actually, doing all the testing and stuff.
Okay. Okay.
So
Yeah. Maybe we can talk by the end of this month, and if not, we can do it at the beginning of
right,
October.
right, yeah,
Don't worry.
yeah. Um, we'll figure that out. All right. So cool. So at this point, still TBD. Great. Yeah.
Yeah.
So I guess we only have, geez, we're running out of 2025 pretty quick, right? We just have October and November and December, and then that's it. All right. Well, great. Okay. So that's about it in terms of the announcements here. So getting into the meat of it. So I'm still chipping away at the rewrite into System Verilog. There's a number of modules that I've committed over well, I guess last week or week before last, pretty recently, a bunch of AXI stuff, and I'm starting to get some DMA stuff pushed over there as well. Um, they're also working on a release of CocoaTB 2.0, which has some breaking changes. So I've had to go through and make some adjustments to the test benches as well as to all of the CocoaTB extensions to get everything prepared for the 2.0 release. And there's also a couple of things that I've added to CocoaTBX to AXI. So I'll talk about that a little bit in a minute. Primarily APB is now supported, hopefully. It's not thoroughly tested yet, but it's there. Also been adding a bunch of stuff to the taxi library. I mean, that's basically just the rewrite progress. And then I've also been doing some more stuff with time synchronization. So I think I'll, glance over some of the low latency stuff because there hasn't been much movement on that. But I've just over the past couple of days have been doing some testing with 100 gig links and the DDMTD, and I mean, it's working. It's not quite as fine-tuned as I would like, but one step at a time. And then I got a few updates on Corundum and on the Zircon stack. So let's go ahead and get into it here. So mentioned this at all the previous meetings here recently. I'm working on a rewrite of basically Corundum and all of the supporting libraries into System Verilog and switching to the CERN OHL strongly reciprocal license. So if you're interested in using some of the stuff for commercial applications, reach out about licensing and we can figure something out. I can offer support and whatnot on a long-term basis. Um, so I have System Verilog interfaces for AXI, AXI Stream, AXI Lite. I'm adding some stuff for PCI Express and for DMA. Um, the porting of the core library modules is progressing, which I'll talk about that a little bit more in another slide. But I'm getting more AXI, AXI Lite stuff ported over. Most of the AXI Stream stuff is done at this point, and PCI Express and DMA stuff is I think next up on the chopping block. And we have a lot of new code as well in terms of more refined Mac PCS and transceiver wrappers for 10 gig and 25 gig. And at some point, I'm also going to be extending that hopefully to 1 gig and 100 gig. And I have example designs for a bunch of different boards. I added a couple more of those over the past couple of weeks as well. All right, so porting progress. Yeah, AXI Stream's basically done. I've been doing a bit more work with recently with AXI and AXI Lite and some of the DMA and PCIe components. So still lots of little stuff on the to-do items, but um, at least on the AXI Stream side, and for the Ethernet Max, all that's been ported over and all seems to be working pretty well. All right, so I've also been putting together example designs. The plan is to have sort of per subsystem design, so kind of similar to what I had previously with the separate libraries, where each one kind of had its own set of example designs. So with Taxi will be pretty similar. But because everything is all in the same library, it should be easier to do some cross-pollination. So for example, most of the example designs are going to use XFCP for diagnostics, so you can read statistics counters and change settings and things of that nature. Most recently, I updated the ZC111 example design to add the RFDC data converter support and all the PLL initialization and whatnot. All pure HDL, no Peta Linux involved. And then I also added the QSFP28 FMC for the High-Tech Global ATG 9200 board. So that includes, again, all the PLL initialization to make that work. The main to-do, I guess, for the example designs is adding support for some of the Intel parts. So at some point, I'll get around to that. It might be a little while. We'll see. All right, so moving on to CocoaTV 2.0. This is something that I can't remember exactly when they're trying to cut the release for CocoaTV 2.0. They're trying to get it to coincide with, I think, some sort of conference in the next week or two. And as part of that, I'm going through and making sure that all of the test benches and stuff and all of the CocoaTV extensions run properly with the development version of CocoaTV. So I've cut new releases for the UART, I2C, AXI, and PCIe extensions. There is a minor issue with the Ethernet one. We basically need to figure out whose bug it is, right? If it's a CocoaTV bug, then it should be fixed there. If it's me doing something wrong in the extension, then we need to fix it there. Basically, it's one of the test cases is bailing out with a complaint from the CocoaTV scheduler, and it's basically a question of am I doing something wrong, or is there some bookkeeping issue in CocoaTV that's resulting in the scheduler complaining? So hopefully within the next few days, we'll figure that out, and I'll cut a release for CocoaTVX Ethernet as well. There's a couple of other issues that I need to sort out due to changes in CocoaTV 2.0. One of them is I have some packed versus unpacked array issues that need to be sorted out in the HDL. Because basically with the CocoaTV 1.9.2, you can, if you have like a packed array of clocks, you can, listen to each bit separately for edges or whatever. But for CocoaTV 2.0, they've removed that because indexing unpacked arrays like that doesn't work particularly well in many simulators. So I need to go through and basically switch up how I'm doing stuff. So either we have a top level HDL file that pulls the signals apart where CocoaTV can connect to them, or I have to switch to using unpacked arrays instead of packed arrays. So there's a handful of modules that affects. I think it's mainly the transceiver wrapper stuff for ultrascale. Everything else just uses single clocks and stuff. There's also some sort of issue related to unpacked array assignments. Again, need to figure out whose bug it is. Am I doing something wrong? Is it a Verilator issue, a CocoaTV issue? Not sure. But that's a longer term thing to figure out. I also added APB support to CocoaTVX to AXI. The main reason for that is I'm thinking about replacing the kind of screwy register interface thing that I cooked up with something a little bit more standard. So APB is a very simple mechanism for basically poking at registers. So I've gone ahead and put together a model for that CocoaTVX to AXI. It seems to be working, but then again, I have not tested any of that against the hardware. So I'm not 100% sure if it's correct. Yeah, the way I like to develop stuff is that it's got to be grounded in the actual hardware. Otherwise, what's the point? So I kind of liken it to, if you want to make a really flat surface, if you take two pieces of material and you rub them together, you'll end up with potentially something curved one way or the other. If you want to get a truly flat surface, you got to get three pieces and rub them together in pairs in order to get, the properly flat surface. So you get kind of the simulation model is one piece, the HDL is the third piece, and then the actual implementation in hardware is the simulation model is the first piece, the HDL is the second piece, and then the actual implementation and hardware testing is the third piece. And by doing all three of those, you can actually get a design that's going to work properly. So for the APB stuff, I've only done simulation testing so far. So um, there may be some bugs in it that'll have to be fixed, but it is there if people want to start hammering on it. Um, all right, so moving on to the taxi library itself, there's a bunch of stuff that I've been working on porting. I've gone ahead and ported over some of the ultra-scale specific PCIe stuff. I was originally thinking about just tossing that and only using the more generic stuff, but I think especially if you're trying to build something small footprint, it makes sense to use the ultra scale specific stuff. So for like Corundum Micro, it would make sense to use the ultra scale specific like AXI Light Master and DMA related code. So and there's also some issues that I need to sort out in terms of porting the full um, generic stuff. It's a little bit more complicated, especially with the wide segmented FIFOs and such. So we're going to start with porting the ultra scale specific stuff, and then once that works, then I'll port the wider stuff, the more generic stuff. So I've tested that one in the hardware on a couple different boards and seems to be working fine for the moment. It'll be more interesting, I think, once I get some of the DMA components ported. I'm in the process of putting together the interface components for that. The system Verilog interfaces and getting all the parameterization figured out um, before I port the DMA components. I also went ahead and got a bunch of AXI stuff ported over and pushed up. I have the AXI light width converter, which is looking pretty good. I have AXI to AXIL and vice versa adapters. I also have the somewhat crappy AXI width converter that I put together. That's up there as well. I figure even though it's slightly crappy, I'll just get what I have up now, so it's usable, and then at some point down the road it can be reworked. But I think also it's one of these things where reworking it is going to make it a lot bigger. It's going to improve the performance and improve the flexibility, but it's also going to increase the footprint. So it might make sense to keep a couple different variations around depending. I've also pushed up a few DMA components. Let's see. So I have the system Verilog interface for the segmented RAM. I have the segmented RAM itself. I have some simulation components related to that. Things that are going to be necessary for getting the DMA, the rest of the DMA components implemented and finalized. I've also been working on a few new modules. So the AXI Stream Slicer module, it's still working on it. It's not done yet. So that's kind of been on the back burner for a little while. And then I've also been working on some APB related stuff. So I have the system Verilog interface that's up there right now. The APB RAMs are actually done, but I haven't put them in the repository yet because I'm waiting on sorting out the rest of the CocoaTB 2.0 stuff. And then I'll go ahead and add those. And then I'm also working on an AXI Lite to APB bridge. So you can actually use some of the APB modules. And there's probably some other related components that I need to build related to APB, but that's kind of the high level status of that for the time being. For example designs, I think I already touched on this. I added a variant of the HTG 9200 for the QSFP28 FMC. That's actually not a separate example design. It's just kind of a parameterization configuration variant of the core HTG 9200. So that's kind of nice, right? It changes the number of transceiver channels and doesn't, I guess there's a separate top level file. Yeah, that includes the additional PLL configuration. So that's kind of a nice setup because it's not like a completely separate design like it was in the previous, Verilog Ethernet setup. I also added, like I said, the RF data converter support to the ZC111 example design, and I added example designs for the HTG ZRF8 EM and R2 with the RF data converters. So it took a while to figure out how to get all the PLLs properly configured for the ZC111 and the EM and R2 boards, but I did finally manage to figure it out, and that's all encoded in the HDL. And like I said, these are all pure HDL designs that do not use the the zinc cores at all, right? It's so there's no pay to Linux or anything like that involved. So depending on what you're doing, that might be an interesting thing to look at. Um, Getting things working on the ZC111 was kind of a pain in the butt because because of how things are wired up on there. It was kind of an interesting project of spending far too long trying to get four LEDs to turn on, um, but finally managed to pull it off. Julian has a question, or
Yeah, I was wondering if you actually use the RFDC stuff or not. Not at all.
if I actually use it.
Yeah,
What do you mean?
I mean the RFDC part of the ZCU, all the data converter and all of that.
Yeah,
Yeah.
if I actually use it.
Yes.
Well, I mean, I've only done like some sanity checks where so the design internally it connects the converters back to back, so it just takes the ADC data and stuffs it into the DACs. So you can hook up a test signal to any of the analog inputs and then check, put a scope on the corresponding output and see if you're seeing something reasonable. So aside from that, I haven't done, the example design doesn't really do much with the data converters. Actually, I guess there's one other thing in there. I added some mark debug stuff so you can easily attach ILAs and monitor the data converters. Um, but yeah, I don't have like an SDR design or something like that at the moment.
Okay.
I think what I might be doing at some point, I was kind of mulling over whether I should do this as part of the research stuff, as I have this DSP debug block, which is basically just it's a very small segmented RAM with a little register interface, and it allows you to either capture, it's got AXI stream in, AXI stream out, and either you can capture the data as it's passing through into a little buffer and then read it out, or you can load up the buffer and then have it, kind of do a waveform generation and play it back. So what at some point I think I'm going to make a slightly more refined version of that core, and then I'll add that to the example design. So you can actually do, somewhat rudimentary waveform generation and data capture um, with the ZC111 design. But it's probably going to be a little while before that's there. Or did you have anything in particular in mind with the data converters that you'd like to see?
No, just because I had the occasion to use it recently, and so I was just wondering.
Okay. Yeah, so we're not using the ZC111 for anything at the moment, but we are using the ZRF8 EM and R2. Um, so we have some other code that sits on top of those. Um, Now I guess that code is not actually built on top of Taxi at the moment. It's built on top of Corundum. Um, but I figure I would get everything, set up with Taxi first, which is, there's not as much infrastructure, right? We don't have all the PCIe stuff with the Ethernet, with the Taxi Ethernet design. So it'll be a little bit simpler to get it working there. And then later on, we can shift it over. And that worked out nicely. Just copy and paste basically. And then it worked um, for the Corundum version. But yeah, so I think for all the stuff that we're doing right now, we're not doing like RF stuff. It's actually somewhat low frequency, um, which has been a bit of an issue, like because a lot of these boards they have baluns that have a pretty high low frequency cutoff. So if we're trying to do stuff in the megahertz with these things, that becomes a bit of a problem. And yeah, the EM in particular, they I thought all of these boards had basically the same front ends, right? The ZRF8, ZRF8 R2, and ZRF8 EM, but it turns out they have, well, there's some difference with the EM. I think the difference that I'm seeing is related to different size DC blocking caps. They seem to use 100 nano on the R2 and 10 nano on the EM. Um, but I haven't pulled out a soldering iron yet to swap them out and confirm that that's actually what the difference is there. Anyway, getting off on a tangent here. So those example designs should all be available. Yeah, they might be good references if you're working with a similar board. All right, so the AXI Stream Slicer, I guess I talked about this previously. The idea is you can specify the offset and length of a portion of a packet on an AXI Stream interface, and then the slicer will extract that. It'll shift it around to remove whatever's in front and then clear out whatever's after. Currently, what I have only works for, single byte wide interfaces. Got to start with that first, get it working there, and then you can work on the wider stuff. And I also need to implement some better handling of sideband signals. But yeah, so at some point, hopefully in the next few weeks, I'll get around to improving this situation here, so this can actually work at higher throughputs. All right, so I have the new Mac GT wrapper. Not much has changed here, so I'm just going to skip over these. And the low latency mode, I actually have not been doing much with this recently. I think right now all the example designs have been updated to use this mode by default, mainly because it's a better test for timing closure and whatnot. It runs at a slightly higher frequency. Um, but yeah, so for the stuff that's running on Corundum, we're not using the new wrappers there because system Verilog versus Verilog. So yeah, at some point, once we have the new infrastructure in place, then that'll be properly integrated into Corundum and we'll be able to use it. So yeah, like I said, for all the research stuff, that's built on top of Corundum. So we're using, the wrappers that are part of Corundum and not the low latency ones. All right, so there's also the 32-bit Mac and PCS. If you're doing 10 gig stuff, this is a smaller footprint, which is always nice and also lower latency. Did I do any? Well, so there was somebody that did a bunch of latency measurements, but I guess they haven't done another one for the new 32-bit cores yet. I think I might have some numbers from my network tester, but yeah, I think the network tester I have is maybe not. It gives you numbers in microseconds to only a couple of significant places. So yeah, I'll have to think about how to do a proper latency measurement of all of these cores. And then when I do that, I'll certainly let you guys know what the numbers look like. Okay, yeah, talking about the latency, or not the latency, the footprint. Yeah, it's 64-bit versus 32-bit, 50% LUT savings and a 25% flip-flop savings. That's pretty significant. So yeah, if you don't need 25 gig and your design is simple enough to where you can close timing at 322 megahertz or whatever, then the 32-bit core definitely is a good thing to consider. Okay, so a while ago I did a rough 25 gig Syncy demo on an Alview U200. This was kind of a totally hacked together design where I basically just put the new Taxi Mac and PCS wrappers in front of Corundum. Didn't even bother connecting any of the data, just the clocks, and was able to get to collect some performance information about what things were looking like. So the PLL loop successfully locked, but it ended up being a little bit noisy. So this is okay. This is with the normal latency variant, I guess from Corundum, and this is with the low latency variant, but also with a bunch of fiber added. So it's slanted because the fiber was heating up or cooling down or whatever. Basically built a very expensive thermometer. So that looks, it looks pretty reasonable because we can still pull out these steps down to a couple of picoseconds, but obviously it's a bit noisy, so there is some room for improvement there. But to figure out where that noise is coming from and if there's any reasonable technique to mitigate it. Maybe just more averaging, not sure. But the other thing that I noticed is this temperature dependent step stuff. I have not had a chance to dig into this further, but this seems to be related to the buffer bypass logic and the delay line in there moving between different taps as the delay through the device varies. So yeah, this is definitely going to require some more experimentation, I think, to figure out if there's a solution for this, because these taps are not so great when it comes to trying to do high precision time synchronization. There was a presentation out of well, it wasn't out of CERN. It was a different it was physics related, a different accelerator setup. But it was, I think, at the FPGA developer conference at CERN earlier this year where it was presented, where they talked about doing, I think it was frame synchronization or recovering the frame clock at the receiver using, the Xilinx UltraScale devices or whatever. And that involved some relatively low-level manipulation of some of the internal transceiver components. And the presentation actually had some, register addresses and things on the DRP interface of stuff that isn't particularly well documented. So there's definitely some stuff here that's worth exploring. So that's probably going to be a longer term thing to take a look at. What could potentially be done here in terms of the buffer bypass logic? Is there a different way to drive this delay line, basically, that might either reduce the number of steps or, maybe smooth stuff out a little bit in some way? Like maybe if you can't reduce the number of steps, maybe doing some sort of dithering over, if you do something on a shorter time scale, then that might end up producing a better result over the long term. But we'll see. Yeah, so the steps that I was seeing are about 15 picoseconds, and I think that particular presentation had some information about the buffer bypass circuit that indicates that the step size of that delay line are on the order of 15 picoseconds. So things are lining up for that being the source, and yeah, not sure if there's much that could be done about that. All right. So I guess one other thing that, as I was thinking about all this time synchronization stuff and talking with a couple of the folks at CERN, I came to the realization that 32-bit 10 gig and 80-bit 25 gig both operate at 322 megahertz internal to the FPGA. So if we do some weird custom gearbox from 32 or from 32 bits to 66 bits or 80 bits to 66 bits, then we could potentially do, a really nice time synchronization setup where everything is all running on the same internal clock frequency, at least in terms of, the DDMTD and time synchronization components. Obviously, the data path itself would have to run at a different speed, but, if we're interested in the time sync performance, that would be probably a pretty reasonable trade-off. So at some point, I might be looking into this in a little bit more detail. So for the work that I'm doing here at UMD, we're trying to use 100 gig links. So what we were looking at is, can we do, White Rabbit type time synchronization over 100 gig link? And the first thing to try there is, okay, can we do basically synchronous Ethernet using the DDMTD logic? So I got it set up. I was originally going to do it between the R2 and the EM, the ZRF8 boards, but there seems to be a signal integrity issue on the EM, and I was having really hard time getting the 100 gig link to work reliably. And then when it did work, I was getting really noisy, crappy results out of DDMTD. So what I ended up doing is using an Alveo U200 for one end, and then the ZRF8R2 for the other end. Basically with the default CMAX setup. So it's not in buffer bypass, it's not the low latency configuration mode, just to see what things look like. And well, the software PLL loop does successfully lock and track, and it's a lot better than with the R2 and the EM. But the DDMTD output is still a bit noisy. It seems to be a bit worse than 25 gig demo. So I don't know why it would be, because the transceivers should be in a very similar configuration, but it'll require some more poking around to see if I can figure out what to do, if it can be improved. So that's kind of what we're looking like here. Unfortunately, I don't have my nice programmable delay line here. Actually, I guess the one I have, it is technically programmable, but I don't have the right cable to actually generate that little step sequence. So we can just look at kind of the overall, you know, noise performance here, basically. So I think top to bottom is something like 80 picoseconds, right? So this is 1.07 nano to 1.15 nano. So that's about 80 picoseconds, and then 10 picoseconds or so is, you know, a good bound on the averaged data. So yeah, we can definitely still pick out steps of, 5 or 10 picoseconds with something like this, but it definitely seems to be a bit worse than operation at 10 gig and 25 gig. But yeah, like I said, I don't know why there'd be a significant difference between 100 gig and 25 gig when they're both running at the same bit rate. So that's going to require some more investigation to get to the bottom of. All right. So, but this is promising, right? Because if Syncy works, then it should ostensibly be possible to do White Rabbit over 100 gig link as well. It's just a question of how to do the timestamping and at the packet level, because at 100 gig that's much more complicated than at 10 gig or 25 gig. So I'm probably going to have to, if we do end up going that route, re-implement some portion of the 100 gig PCS at least to be able to detect packet starts. So we'll see. I don't know how feasible that's going to be, but that's definitely a longer term project. It would be really cool to pull it off though, and have an actual core for doing White Rabbit over a 100 gig link. All right, so moving on to Corundum. Next generation version, the plan is to build 3 different variants, targeting different optimization points, micro, light, and NG. Micro, the original idea I had was to target like SoCs, where you want something really small with a couple of 1 gig ports. But at the meeting last month, it was brought up that things like TSN can operate at 1 gig, so having a relatively compact design that can support multiple queues and scheduling and whatnot could be a pretty powerful capability. So, all right, well, back to the drawing board here. Would it be possible to extend Corundum Micro to support a wider range of features? And yeah, I mean, I'm a big fan of parameterization, so yeah, I think that should be a reasonable thing to do and actually support, um, for Corundum Micro, we're just talking about, a few gigabits per second tops, but being able to support either SoCs or, a few gigabits per second over PCIe for, other applications, TSN or whatever. That I think would be a very reasonable thing to do. Corundum Lite then is going to be similar in performance to the current version of Corundum, maybe about 100 gigabits per second aggregate throughput. And then Corundum NG, the plan here is to support up to 400 gigs. So we'll see. That's probably going to be a ways down the road before Corundum NG is operational. But the other two, hopefully, should be a little bit more straightforward. And the plan for all of these is to support all of the same basic core features, same driver interface, timestamping, checksumming, and at least scatter gather offloading, maybe segmentation offloading for TCP segments and UFO, that sort of thing. All right, so my thoughts for Corundum Micro is for 1 gigabit per second. Generally, that's going to be 8 bits wide at 125 megahertz. So one packet is about 80 bytes long on the wire, right? You get 64 bytes for the packet plus 12 bytes IFG plus another 8 bytes for the preamble, gets you to about 80. So if we're going to share everything, if you do say 4 ports, that TX and RX, that's about 10 cycles per packet, right? 80 divided by, 4 divided by 2, that gets you to about 10 cycles per packet. And then if you extend that up, well, I think 25 gigabits per second throughput, if you run the core at about 400 megahertz and you split TX and RX, so that's a simple replication, that should get you to the 25 gig line rate with the minimum packet size. So seems to me like that might be a reasonable sort of range for Corundum Micro to operate at, right? From a few ports at 1 gig up to maybe 2 ports at 10 gig or 1 port at 25 gig. I think something like that should be doable. Now, you have to run at like 400 megahertz to get 25 gig line rate, so you'd have to do a CDC on the PCIe end for that to work. But yeah, we'll see about the details. At least the numbers seem to work out reasonably well. So that seems like it should be doable. And then also the idea would be to support both AXI and PCIe for the host interface, so you can run it on a PCIe card or whatever. And then again to support all the basic NIC offloading and whatnot. But yeah, one of the main reasons for building Corundum Micro as well is that it's going to be a good mechanism for prototyping the new driver interface and getting the new driver operational. Because it's a lot easier if you have a bunch of cycles to play around with. You don't need to pipeline the heck out of everything. You can get it working with the relatively simple design. And then once we have the driver figured out, then we can look at ramping up the performance for Corundum Lite and Corundum NG. All right, so again, for Corundum Lite, we're talking about 100 gigabits per second throughput aggregate, so 1 or 2 cycles per packet. I think 100 gig, if that corresponds to like 148 million packets per second. So if you run the core at 250 megahertz, then you basically only have 1 and change cycles per packet. If you run the core at 300 megahertz or something, then that gives you 2 cycles per packet. So yeah, that's it's doable, but I think not too crazy, right? 1 cycle, as long as you're not trying to do multiple cycles or multiple packets per cycle, this I think is pretty reasonable. Corundum Lite, the plan is to support multiple TX and RX queues and SRIOV. I guess I forgot to mention that before. With Corundum Micro, the idea is to have an option for multiple queues and scheduling, not necessarily SRIOV support, but multiple queues and scheduling that you can turn on. If you want, obviously it'll take up more logic resources, but then it'll give you the ability to do TSN and that sort of thing. Corundum Lite, the idea is that it's going to support multiple TX and RX queues natively, and hopefully also support SRIOV. That's one of the reasons for building Zircon as well. It's like for SRIOV on the receive side, you have to do some filtering and classification to figure out where to send packets, and maybe even replication for broadcast and multicast, things like that. So for SRIOV support, it's one thing to add that on the PCIe side. It's another thing to actually make it usable by having the network side of it implemented. So the idea with the Zircon stack is that can provide the network side of the SRIOV capability, and potentially also enable similar stuff for like AFXDP. And again, Corundum Lite will support both PCIe and AXI for the host interface. And I'm also going to look into some sort of a dual head thing where if you have an MPSoC PCIe board, maybe you want to have both the host and the SoC connected, in which case the SoC would kind of be acting like a PCIe VF sort of, but not exactly. It would be treated like that from the management standpoint. And the plan with Corundum Lite is probably to support the application section and hopefully also make it available as a standalone self-contained core as opposed to just a top-level design. There's definitely some advantages of having everything kind of a top-level design where you can have an application section that you can run on multiple different boards, but for other designs, it makes more sense to have a core you can just drop in. So definitely supporting that is going to be on the to-do list. And then Corundum NG is just pull out all the stops, multiple packets per cycle. Let's see how fast we can go. Multiple ports at 100 gig or, single port 400 gig, that sort of thing. This will be built on the Agilex R tile. And I'm also going to probably be taking a look at multi-headed PCIe. I think on like the V80 boards from Xilinx. Those, what was the deal with those? They don't support Gen 5 by 16, but they do support, dual bifurcated Gen 5 by 8. So, hey, it'd be great if you could use that and get the full throughput. So we'll probably look at that as well. But again, this is going to be down the road a ways, probably. And this one, probably also going to look at the PCIe AXI dual head again for Zinc and Versal type applications. that would be a useful capability to have. And then also probably local AXI DMA for DRAM, HBM type stuff. So you can transfer packets just directly into on-card memory as opposed to sending everything to the host. And also just being able to have some of more generic interface to the DMA for if you have a accelerator type card, hey, can you DMA memory from the host to the card as opposed to only having the DMA available for networking stuff. That would be a useful capability as well. All right. And then the last thing, Zircon, the new network stack that I'm chipping away at. The idea is that this is going to be a replacement for the old UDP/IP stack that I have in Verilog Ethernet, but it's going to be more of a socket style interface where you can, have this explicit connection state that gets tracked by the core, and then the ability to track, quite a few of these connections going in parallel. So internally, it's going to have hash tables and some other relatively complex components to keep track of all this, as well as the ability to parse relatively complex packet headers. But yeah, the idea is that this can be used standalone. It can be used with Corundum as a front end for SRIOV, and you'd also be able to use it kind of in a hybrid mode where you'd have, some of the client ports of the Zircon stack going to the FPGA fabric for whatever your custom design is, and then maybe have Corundum as well for somewhat low bandwidth, management type stuff. Maybe you want to have a little soft core that does some management stuff, use, Corundum Lite connected to Zircon, and then have, maybe 100 gig data path to your application logic on the FPGA. That's kind of how I envision stuff working. So getting all of the plumbing figured out is still a bit TBD, but that's kind of the long-term goal that I have for the Zircon stack. So I guess I've talked about how I envision the stack working here, where we have streaming interfaces for each client, where you have data TX and RX and control TX and RX. By having the separate interfaces, that is going to reduce issues with headline blocking. And then by having these control TX and RX interfaces, instead of doing everything with registers, it means that we can potentially significantly change the internal construction of the stack, potentially just based on how you parameterize it. And then you don't need to worry about those details when you're interfacing with the stack from the user logic. It's kind of a similar setup to Corundum, where we use the the command queues for the new version of Corundum, where I'm going to be using command queues for allocating queues and performing various management functions instead of having a big complicated register interface, because that's going to be a lot easier to kind of remap these abstract operations onto the specific operations that need to be performed for that particular configuration of the design. And then the client interfaces, they can carry data in different formats. You could either get just the full packet, you can get just the UDP payload. I'm also thinking that there needs to be something kind of intermediate where you have some very simplified regular headers that can be easily turned around. So you can do kind of more of a stateless communication without having to allocate the internal connection state for each connection. So that piece I'm kind of trying to figure out right now, because for some applications I think that's going to make a lot more sense than putting everything into the internal connection state. As I talked about this previously, the UDP client example, so I'm not going to go over this in detail unless somebody wants me to. The status right now, the initial implementation is going to target 10 gig, 32 bits. The parser and deparser logic that I have is going to be fixed at 32 bits. For higher rates, you replicate. For lower rates, we'll do with conversion. So the footprint will be a little bit higher, I guess, than if you did, 8-bit stuff, but it makes it a little bit easier to manage. Maybe we can revisit that later if need be. The parser and deparser are mostly working. I'm working on the internal data path and rules engine, and I have an early prototype that's tested in the hardware. It's got I think, a few minor timing closure issues to sort out, but for the most part, it does what it's supposed to by echoing back packets with with reconstructed headers. So we got the parser, the deparser. I guess I'm not going to go into this in too much detail, as I talked about that the last time around. But with the basic, so loopback echo test design, it will extract the payload from a packet of whatever format, right? I think this one is an ARP packet, so it pulls the payload out of that and then echoes it back as a UDP packet. I mean, obviously this is not particularly useful, but it does show that the parser can figure out the headers and extract the payload, and then the deparser can build all of the headers from scratch and compute all the checksums and everything, and send the packet back out. So I got to do some more work on the control path in order before you'll be able to do like a proper UDP echo test. But that's definitely on the to-do list. I think that about rounds it out for everything that I have to talk about. Yeah. So if anyone has any questions or comments, go ahead and fire away.
Do do you have any pointers where I can look into implementation of SRIOV, which is closest helpful resource in this case?
Like on what level are we talking about here? On the PCIe side, on the Ethernet
The
side, on
PCI
the
side, PCI side.
Uh, yes, I've kind of been trying to get my head wrapped around that as well, because they don't talk about it much in the main PCIe specification. There's a separate specification for SRIOV. I was not able to find the proper specification online last time I looked, but I was able to find like a red line version of it. Um, and I don't know if there's any other, better documentation available aside from the SRIOV spec. Um, yeah, I think I think to really get your head wrapped around it, you probably have to look at both the PCIe spec and the SRIOV, supplement,
Because
basically.
because in the early meetings you said that let's look at some implementation which exists in the wild and because that would probably help
Well, right. So
to
there's a few
gauge.
different aspects of SRIOV. So by looking at existing implementations, I'm actually thinking more on the networking side, right? Because like I
Mm,
said, there's two different aspects. There's multiple aspects to what you need to do for something like SRIOV, right? One of them is supporting multiple PCIe functions, or one of them supporting these virtual functions on the PCIe side. The other one is
mm,
all of the network management, switching, routing type stuff. And actually, the thing is, even with just normal PCIe functions, you you don't even need SRIOV to still maybe need some of the networking, switching, routing type stuff. SRIOV, really, it's just a lightweight way of providing a whole bunch of PCIe functions.
mhm,
Only to virtualized operating systems, because the idea behind SRIOV is every PCIe function, it needs configuration space, right? And that takes
mhm,
up hardware resources to implement that. There's a limited amount of configuration space that's available, and you need to implement all those registers and whatnot. So with SRIOV, the idea is that you implement the VF config space in the hypervisor, not
mhm,
in the hardware. So the hypervisor is actually implementing the the config space for the VFs, but you still need all of the right, PCIe routing and whatnot. Every VF does need to get its own function number and potentially device number as well. I guess once you go beyond, no, I can't remember how big these numbers are. I guess it's 8 functions and 32 devices, something like that. So once you go beyond 8 functions, then you got to start using device numbers for you got to start using the device number space for, more VFs. And then I think
mhm.
eventually, so that'll get you up to 256. And then to go beyond that, you got to start using bus numbers. So um every VF needs to have its own, PCIe ID, such that at the at the IOMMU level, you can isolate things, right? Because
Hmm.
each VM needs to be isolated from the other ones. So
Hmm.
with so from the standpoint of the IOMMU, the VFs have to look like normal PCIe functions.
Right.
But then from
But
software,
but
the idea with the VFs is that it's a lighter weight implementation from the hardware end.
but then I have so from the host operating system, it also has access to PF as well, right? You also see PF and bunch of VF, or you only see VFs.
Uh well, yeah. Well, you have to have PFs, right? The
Yes,
uh the the
and
the SRIOV capability has to live somewhere, and that lives in a
mm,
PF. So basically what happens is well, I guess the question is this is where things get a little bit complicated here because it depends on, what kind of a hypervisor VM setup you're using. So if you use a hypervisor based system, then the operating system isn't necessarily going to touch any of the PCIe config space. That'll be handled by the hypervisor. If you're using something, I guess, maybe a little bit more like a traditional VM, then you might have your, Linux host system, and then you have guests running underneath that, where Linux would be handling where that Linux host system would be handling the PFs. But
but
yeah, obviously you
are
need the
they
PF initially to configure everything, and to set up the VFs, and then the VFs can be handed off to the VMs separately.
are these all handled by VirtIO driver, or VirtIO driver is never in the picture? Because I can have VirtIO driver
So,
take
so
care
I
of.
think so. My understanding of VirtIO is that that's somewhat tangential, right? VirtIO is it's like the VirtIO is kind of like NVMe, right? It's a specification about how a given device behaves. And that's actually a good
Hmm.
point you mentioned VirtIO because um it's potentially possible to expose like the VFs as VirtIO network devices instead of
Hmm.
something more specialized, right?
Right.
So that
Mm.
then means that you wouldn't necessarily need any additional driver at the operating system
Right.
level
Right.
to talk to
Right.
the VFs, or to talk to the NIC. So I've heard of some people thinking about that. Well, hey, could we just build a VirtIO NIC that wouldn't require its own customized driver? And yeah. Um, there's some weird stuff about VirtIO though. It requires a bunch of oddball things in the config space for it to work. So I don't know how realistic it would be to implement that. But for VFs, it might not be too bad. But to do it in hardware, that could be a problem. Um, that's something that needs to be looked into. But yeah, that's somewhat tangential. And I actually don't know, like if you have a bunch of VFs, do they all have to be exactly the same, or could the VFs be, totally different, right? Could we have a set of VFs that are, um, a custom interface basically, and a set of VFs that are VFIO? I don't know. That's that might be
Yes.
possible as well. Then you could send different ones to different VMs depending on what they want.
Right.
Yeah, so that's one aspect of it. The other aspect of it is uh how all of the filtering and stuff is handled, right? Because the whole idea behind SRIOV is every single one of those VFs is going to act like its own NIC, basically, right? And
Mm.
when you have a bunch of NICs, each NIC is going to have its own switch port, right?
Mm.
But in this case, they're all on the same NIC. So what do you need? You need like some kind of virtual switch, basically, to sit between the VFs and the actual network port.
Mm.
So that's what the
To
Zircon
schedule.
stack would be for, is it kind of sits in that level and it's like a packet shows up. It's like, well, what do I do with this, right? It's like previously with Corundum, it's like a packet shows up, you just hand it off to the host, right? You do RSS,
Mm.
pick an RxQ, done. Simple. But with
Mm.
with SRIOV, right? A packet shows up. What do you do with it, right? You want to make sure that you're sending that packet to the correct host. It's like, so I the simple thing to do is you put each VF in a different VLAN, basically. But usually you don't use VLANs that way, right? You might have a VLAN for control and a different VLAN for something else. So, you really have to start looking at, MAC address, IP address, that sort of thing to figure out where to send that packet. Um, and that's a non-trivial thing to do, right? You need a proper, network stack in hardware or a packet switch type capabilities in hardware for that to work. And Corundum hasn't had something like that. So it's like, all right, well, if we implement that as a stack that we could use for multiple things, including this, then that could be a pretty useful capability. And then if you do that right, then it opens up fun stuff where you can have, both the stack connected to the host with, SRIOV and that sort of thing, and then also have hardware clients as well. And then you can mix and match, and the stack can route across everything.
So, why can't I just just asking a random question. So why can't I just match with all the IP and MAC addresses of all the other virtual NICs that exist in my own system, such that if I receive a packet from some VM, if I have to just pass it to another VM, I can do that. But anything else, I can just throw it on the network, on the wire. And maybe on the other side, switch will take care, or
Well, so
whoever
so
it
the
belongs to will
so
receive.
the reason you don't do that as isolation, right? If you're sending packets to the wrong VM, then that VM, if it's malicious, right, it can capture that data and do something with it, right? If you don't want to be sending, well, you don't want to be sending traffic to hosts that are not the intended recipient, right?
All right.
Right? That's
Yeah.
the whole point of isolation is we want this thing to act like a bunch of physically separate computers with their own dedicated hardware. If we have to be bouncing stuff around between the hosts because our implementation is borked, then that's not a good thing. And the other thing with SRIOV is that it's to remove load from the hypervisor, right? Before SRIOV, how would you do this? Well, you would use software switching, right? The packets would come
Yes.
in, they would
Yes.
all get sent to the hypervisor. The hypervisor would then have to look at every single packet and determine what VM to send it to, right? So if you don't have filtering in hardware, that's really the only option that you have is you do that in the hardware. Yeah, and that's again, not not an optimal solution because you got to spend a lot of CPU cycles copying data around, right? Because then you got to start worrying about, memory protection and whatnot. Like, how do you move data from one virtual machine to another, right? With VFs, each VM has its own internal allocation of host memory, right? So the packets come in, they go straight into the memory that's associated with that VM.
Right.
And it's, you get very good performance. If you have your hypervisor
Right.
sitting in the middle, well, okay, well, what happens? The data comes in, it's associated with the hypervisor. So are we going to have to like hand those pages off to the VF somehow or to the VM somehow? Or does the hypervisor have to copy that data and waste a bunch of CPU cycles? It's a bit tricky. Yeah, I'm not actually sure really what the
Right.
state of the art was for, software switching like that between, a NIC and the hypervisor. So
Right.
it's one of these things where things start getting quite complicated when you start when you even dig in just a little bit. So yeah,
So OpenNIC implements, right? I think OpenNIC claims to implement SRV. I have not tested though.
OpenNIC is QDMA. So yeah, in QDMA you can create VFs, but I don't think OpenNIC does anything beyond that really. They don't have any kind of filtering. So last time I looked at OpenNIC, they didn't do any timestamping. They didn't have any filtering capabilities, anything like that. It's basically just an HDL wrapper around the QDMA and a custom driver for QDMA, and that's it. So I didn't even consider OpenNIC as a project necessarily. It's just QDMA with a custom driver. So which means OpenNIC's kind of a misnomer, right? Because QDMA is completely closed. So you can't go in and
Of
change how the
course.
descriptors work or whatever. So yeah.
Yeah.
Anyway, it looks like there's some activity in the chat here. What is going on? I've Let's see here. People have asked some stuff. So somebody asked, is Zircon parser influenced by or related to the P4 language in any way? I'm not very familiar with P4, so no, but I think there's probably some influence on some level in terms of maybe we've kind of developed something nominally similar in terms of how the the separation of actually parsing stuff and building up the metadata works. I'm not sure. I should probably take a look at that at some point. Obviously, we could do something. There are P4 to Verilog solutions, um, but it's been a while since I've looked into those. My idea is to start out with something really simple and see how that works, and then potentially we can iterate on that if we need something more complicated or more reconfigurable or whatever. And then, yeah, okay, for SRIOV, often ARI is used. So ARI, for those of you not aware, is basically it just says screw device numbers. We're going to make it all function numbers. um, it doesn't really change much in terms of how the actual PCI Express setup works. It just takes these few bits that were used. Okay, so the whole device and function number thing, I guess, goes all the way back to the days of PCI, where you have multiple cards installed in a backplane, right? So the way things were set up in PCI is how did it work? How did it work? There is a device select pin in every slot, and that slot is wired to a different address line in every slot, right? So the first one might be wired to address line 0, the next one wired to address line 1, address line 2, address line 3, so on and so forth. So when you do a config access to a device, you basically put a one-hot encoding of the device number on the address bus, and that selects one of the cards. So for PCI, they have, I guess, a 7-bit function number, and then no, a 3-bit function number and a 5-bit device number. So each card can implement up to 8 functions, and then you can have up to 32 cards in a backplane, and you can independently address the config space on each of them. Now, PCI Express doesn't have this shared backplane anymore. So instead, all the routing in PCI Express is done by the bus number. So the device numbers aren't, for a long time, were not really used for anything aside from inside of a PCIe switch. You might use the device numbers to identify the different ports potentially, but that's like the only thing you would use it for. But yeah, so with ARI, that's okay. Well, we have these free 5 bits here, and we would like to be able to use them. ARI just says, hey, okay, if you want more than 8 functions, then you just start using device number bits as well. And then eventually somebody said, well, what if we want more than 256 functions? Okay, great. Let's start using bus numbers too. So, yeah, if you have a device with, 1024 VFs, yeah, you got to use some bus number bits in order to expand the space for that. So yeah, I know some of the FPGA IP cores do support like 2048 VFs. I want to say like the Intel P-Tile or something maybe supports that. I would need to double check the documentation. No, and then Jack Park says he was an architect for NVMe SSDs before, so he's familiar with VFs, SRIOV, and also MPF. MPF? Not sure what MPF is, but okay. A little difficult to explain it all here. Well, I mean, if you're interested at some point, we could do like one of these Corona
Yeah,
developer meetings. You can talk about it, if that's something that you're interested in.
yeah.
So something we did a long time ago where we had a couple of, guest talks about various things. I know I did some reading about the RDMA spec and talked about that a little bit. But
I saw
yeah,
that video.
that would be really interesting to hear about. Because you can certainly read over the specs and slowly piece stuff together, but it would be useful to have kind of a high level overview. Yeah, but we can certainly talk about that separately if that sounds like something you might be interested in doing. But yeah, I guess getting back to the SRIV discussion, one of the things that I wanted to figure out is, I think that the host side of SRIV is I'm not going to say it's straightforward, but it's pretty clear cut how that's supposed to work, right? Because
Hmm.
it's specified in the PCIe spec and in the SRIOV supplement and all that sort of thing. But what's less clear cut is the network side. So what I would be really interested in is existing NICs that implement SRIOV. How does the network side of it work, right? What can you do? Like, what kind of filtering options are supported? How many filter options can you have? That sort of thing. That would be really interesting to know. Because, if existing NICs can do like, one MAC address per VF, that'd be like, okay, well, that gives you a good, data point on the scalability, right? If they can do like 10 MAC addresses per VF, then it's like, all right, well, we're going to have to put some big hash tables in here. It kind of informs on some level what the architecture needs to look like based on how things need to scale. So that's the kind of stuff I think would be interesting to look at. Now, I don't know how much of this you might be able to determine by looking at device drivers, right? Because obviously this stuff has to be configured somehow, right? So if you were to take a look at, say, a Mellanox NIC, for example, and you turn on SRIOV, well, how is it managed, right? Is that done through the PF? Is that done might an Intel programming manual help? Well, maybe. I don't know. And for what? For one of their NICs? I know there's a while ago I looked at what NIC was it? One of the older Intel ones, 82599, I think. E710? Yeah. Is that available on the Intel site somewhere, or that's actually not something I've looked into recently. I know I looked at some of their one of their older devices, um, but not in any great level of detail. Found it on the internet. Yeah, okay. Well, post on Zulip. I'm sure we'll take a look at it. Yeah, Intel actually makes a fair amount of their documentation available. So, I think it was 82599 that I was looking at. And I think I might have got that from Intel website. Um, or maybe I got it somewhere else, but then it was also on the Intel website. Like I don't know. It's funny the weird stuff you see posted online somewhere. Like there was some chip that somebody posted a question on Reddit asking about, some chip that they were trying to replace and what the value of the bypass caps were. So I'm like, well, okay, let's see if I can find a data sheet for that has the cap, values in a little example schematic or something. So I did a quick search and I found like confidential for BYD only data sheet for a different part, but somebody just posted it on like the TI forums or something. I'm like, that's interesting. Yeah. Um, anyway, yeah, we can E710 certainly looks like something interesting to look at. That's a pretty recent NIC. I'm not sure what the capabilities are of that, but if it supports SRIOV and whatnot, that could be pretty interesting to look at. I know at least one of the Mellanox programming manuals is available, but I don't think it's very comprehensive. I think like the ConnectX-4, they made some level of documentation available, but I think there's a lot of stuff that is just not covered in that manual. And I don't think they have any manuals available for anything newer than the ConnectX-4. And then, yeah, like I said, I also found the 82599, but that's a rather old NIC, and I'm not sure what kind of capabilities it has. And then obviously you have the whole, smart NIC side of things, Pensando and whatnot, where they have very complicated packet processing and switching capabilities on there. But that's a whole different ball game. Obviously, they can do some pretty crazy stuff, but they designed a whole custom chip specifically to do that. So that's not really feasible for, implementing something in Corundum. I mean, it could be a cool research project to do something like that, but the plan here is to do something that's a little bit more, production ready, deployable, that's a good balance between, footprint and capabilities, and provides good
I
performance and is reliable.
I,
What were
I
we gonna say?
wonder how RDMA would work in this scenario, right? Because then not only so for yeah, are you going to use the same queues to also accommodate the RDMA requests, right? Because
Yeah.
for managing a lot of VFs, you might have like sending and receiving queues. You can also use them to accommodate RDMA requests.
Right. Yeah. So this was another reason that I haven't implemented RDMA up until now is because you need to parse all the RDMA packets and hardware and such. And yeah, basically the idea is that you're going to use different queues for different things, right? You might allocate some TX queues for transmitting Ethernet data, some RX queues for receiving Ethernet packet data, and then you might allocate some RDMA queue pairs for performing RDMA operations, right? Um, and somehow you're going to have to handle all that in hardware. You know, what queue is what connection is associated with what queue pair, yada, yada, yada. And then obviously it has to be scalable too, right? Because for RDMA, you need a lot of queue pairs for stuff. So if you have a bunch of
Right,
VFs and each one's opening up a bunch of queue pairs, you know, you can very easily get into the thousands of queue pairs. Um,
right.
so that definitely complicates things. And that's actually one of the reasons I want to move away from having, you know, register space, because with a register space, everything has to end up very regimented in very specific locations. You can't really move things around. But if you have an abstraction layer in there, well, then maybe you can start, you know,
Mm,
caching queue pairs, right? If one hasn't been used in a while, you can kick the state off into, you know, some sort of memory, maybe a buffer in the host, maybe a block of SRAM in the FPGA, something like that. I don't know. And then when some operation is performed, then you can pull that state back potentially.
mm,
So we wouldn't necessarily do that from the get-go, but by having that abstraction layer in there, that and not having a bunch of registers that have to be directly accessible to the host, um, it opens up the possibility for doing fancy stuff like that,
mm.
which can definitely help with the scalability.
So I thought it would be like a low hanging fruit to see from not relatively low hanging fruit, of course, like when you put you are like putting a lot of code in there. So I thought, okay, it must be like a low hanging fruit where Alex might not uh, focus on, and I can look into it and contribute a little bit.
For what?
For the SROE host side.
Right, yeah. Well, I mean, we got to make it work, right? And there's going to be a lot of pieces that are going to be necessary for that. I know. So somebody had actually done a rudimentary implementation of RDMA, or not of RDMA, of
SROE,
SRIOV on top of Corundum a while ago.
yeah, it's a paper,
And
right, from
he did reach
FPGA.
out about possibly bringing some of that code back into Corundum. My plan has been to, once I'm kind of in a position to where we're ready to start looking at SRIOV, it makes sense to reach out and go, okay, well, what do we need to do to make this work, right? What changes do we need to make on the test bench
Hmm.
side of things? What do we need to do on the hardware side of things to make it work? Um, yeah,
It's the
but yeah,
FPGA
that's
paper, right? They submitted to FPGA.
I can't remember what conference it was. It could have been.
OS4C or something like that. That is the name of the paper, I think.
Yeah, maybe. That would not surprise me. Yeah.
Apparently, when
Anyways,
I read their
yeah.
paper, sorry, just mentioning that, apparently, when I read their paper, the bigger, so they did not argue for SROV. Like what they said is, okay, Corundum cannot support multiple ports, which is not true. You can still do it, right? But it's like you can instantiate multiple ports in the same NIC, and like how we have like currently in the current existing Corundum version, right? You
Yeah.
can still instantiate multiple
Yeah, we need to
ports.
take another
But
look at the paper to remind myself exactly what the argument was. Um,
right.
Anyway, I was just going to say, does anyone else have any questions or comments? Or is everyone content with just listening?
Yeah, I don't know if you hear me correctly.
Yeah, I can hear you.
Yeah. Okay, just to tell you that I don't know if the camera will work. Maybe yes.
There we go.
Yeah. I just got myself an AVNet card with an MP sock on it.
Oh,
So if you
nice.
see it. Yeah, and for a very cheap price of zero.
I'm not going to
So,
argue with that.
but yeah, and it's very similar to the ZCU 106, I think, from what I
Mm-hmm.
could see, which is supported on the current Corundum.
Right.
So for now, my plan is to support it on the current version of Corundum just to get me started.
Yeah.
With the environment and all of that, because I need to ramp up on this. And maybe later on, since on this card there is already two SFP plus interface,
Mm-hmm.
one PCI, which I don't know if it is. I don't know yet if it's linked to the PS or PL. I have to check that. And we also have an FMC HPC interface where I would try maybe to put at least one 40 gig interface, to have 4 times 10 gig. And if I can find the right card for it. And
yeah, those things can be kind of hard to find. It's there's not that many FMC boards bouncing around on eBay. I think I saw one from like Reflex CES or something, but it was not particularly cheap.
Yeah, exactly. And I found some, and when I clicked back the day after, it wasn't there anymore. So yeah, I think I have to snipe it at the right time, if I want.
Speaking of sniping stuff on eBay, I somebody had a listing for a couple of XNX X40s, and I'm like, I could buy them. I don't know. They were for a pretty decent price. I probably should have just bought them, but I checked the next day and I couldn't find that listing even under completed. But the same seller had another listing for 4 X40s and 6 X10s for like $800 or $900 or something. I'm like, geez, if I had seen that. That's a lot of hardware. Like new in box too. I'm like, what the hell? So somebody got a very good deal. Wasn't me.
Yeah, absolutely.
But somebody got a very good deal.
So yeah, I need to work on this card to have it working and all of that. I even had to change my my computer because the one I had didn't have enough RAM for Vivado. The Vivado just crashed.
It's kind of a memory hog, yeah.
Yeah. So I had to update, and I still have some work to do on this side, but yeah, I plan to work on all of this on the coming month.
All right, cool. Good to hear. So getting
maybe
new boards is always fun.
Yeah, and maybe at the end I will be able to do a pull request to support this kind of board at least.
Yeah. I think if it's a standard dev board, then that could be be worth looking into. Yeah, I guess.
Yeah, it's
so one thing that I like about
AVNet one.
Yeah. So one thing I like about a bunch of the Xilinx dev boards is that they had like an Ubuntu image that you could download and just stick on an SD card and then boot in the card, which really saves a lot of annoyance because working with Pay to Linux is a big pain in the butt. But well, I guess you said there's a new version of Pay to Linux, right? That's maybe a little bit more flexible.
Yocto.
That's like
Yocto,
just more directly based on Yocto. It might be interesting to get some designs working with that because I have no experience working with that. I mean, obviously I've done some very basic stuff with Pay to Linux, but it's more like, let's just see if we can get this to work, not let's make something super clean. Because I just don't have it's the kind of thing where it almost seems like the software side of things is way more complicated than the hardware side of things. And like Yocto seems like it's, duct tape and baling wire. And it's just a pain in the butt to use. Yeah, I don't know.
Yeah, I think Yocto is already complicated stuff, and if you add Peta Linux on it, it's even worse. So
Yeah.
I'm happy that they are shifting away from Peta Linux and returning back to Yocto. But the issue here is that they have a lot of issue on this due to this new way of doing things. They have a hard time, and also Yocto is changing things all the time, so they have a hard time keeping up as well. So yeah, it's a challenge in itself. And Yocto also is a memory hog. So
Oh yeah, and disk space hog too. Holy crap!
yeah, also yeah, that's even worse.
Yeah,
Yeah, I
I
agree.
can't keep any of the Yocto stuff around because it just takes up way too much freaking disk space, and it also doesn't work over NFS. So we have a couple of
Yeah,
diskless server setups where we have
yeah,
10 or 20 servers or something connected to a UCSD. I don't have this in my garage. I can't afford the
yeah,
power bill. We have like 10 or 20 servers all booting off of one of them. And it works great for the OS side of things, right? Because you can just install a package and reboot everything or update the kernel and reboot everything and it's all in the same state. But freaking
sure.
Peta Linux, you can't build on that setup.
No,
Vivado is fine, right? You can build the FPGA configurations all day long, but Peta Linux, nope. It just
no, you
complains
can't.
bitterly, so kind of annoying.
Yeah, and it's getting better on the Yocto. You know,
Hmm.
on the recent
Yeah.
version of Yocto. I mean.
Yeah, I mean, honestly, so
There's
the
been
one
some
thing,
issues on this.
yeah, the one problem that I ran into is that occasionally, like, I can't figure out how to get it to rebuild things properly. And
Yeah,
the simplest thing to do is just to do like a totally clean and then restart. But the problem is when you clean it, it also deletes like all the downloaded files. And then it's got to
yeah,
re-download everything again. And invariably, you're going to get
yeah,
like 2 or 3 downloads that fail. So then you got to rerun it. It's like, ugh. And it's like it also has to clone a bunch of Git repositories, and it takes way longer to clone those usually than to download all the other stuff. It's
yeah.
like, ugh.
Oh, and
Yeah,
there have
it's
been a lot. A funny thing also is when you are building Yocto, sometimes now you're hitting some kind of limit in GitHub, like you're cloning too much,
oh,
and so you get
you get rate
ejected by
limited.
GitHub, like a rate limited, and so your build fail, and then you come back the next day, you try again, and it works because of course in the meantime it yeah yeah
Yeah, that's
it's
pain.
completely
That's
crazy.
pain.
Yeah, that's a pain. You have to put a download dir on your directory. You have to put some cache and all of that. So. But it's not very often documented. So
Yeah. Well, I
yeah,
mean that's GitHub is not really intended for distributing software. So all of this stuff that
no, not
hooks into
really.
GitHub for build systems or whatever is
So
like, it's
so
not
yeah,
not great.
so yeah, in a lot of company now, they are putting things like JFrog Artifactory or things like this that are of course paying solution.
Hmm.
You know, for storage and local caching and all of that. And most of the time, it just doesn't work correctly. So you still have a problem with that as well. So yeah, it's Yocto. It's always been a pain like this. I don't know how many energy and CPU cycle all around the world are lost just compiling this stuff. It's
Not as much as the AI data centers, but probably a lot.
yeah. So yeah, I agree. But normally, when it's used correctly, you have caching and you only rebuild what you need. But sometimes you have some kind of ununderstandable error. You can't understand what happened when the build failed, and so the quickest things to do is to clean up everything and start again, and it magically
Yeah.
rework again. But so and that's a very big issue in my opinion on Yocto.
Right, yeah.
Yeah. So yeah.
Well, what can you do?
I expect that the Ubuntu image that you were talking about before, I think it should, if it works on the ZCU card, it should work on this one as well, just by changing a few things like the DTS and all of that. But it should
Right,
it
yeah,
should
yeah.
work like that.
I think, yeah, that's one thing that honestly annoys me about a lot of these SoC things is that it seems like you should be able to run like literally the same compiled kernel file on just about anything. But
Yeah.
you need to have the device tree, properly matched
Exactly.
up and potentially some
Yeah.
other config stuff. It's like for
And
like every other computer, it's like, oh, you get the x86 or the x64 version, and then it runs on anything.
yeah.
But for you go to like OpenWRT or something, and they got like every single router has its own build. It's like,
Mm.
why do you need to do that?
And actually, the Raspberry Pi stuff, they are doing
Yeah.
it. I mean, there is some multiple device tree for each one of the board, and you have additional, overlay for the hardware you put on top of it,
Right.
and it works. So yeah, basically, you should. I know that at the time, a long time ago, on the OpenWRT stuff, they were doing that because it was so much memory constrained that they absolutely didn't want to insert neither in memory nor in flash any driver or anything that didn't need.
Right. Yeah, that makes sense.
Because of course they were so memory constrained. But nowadays, I mean, it has no sense.
Yeah, I guess it's probably more just the hardware has evolved a bit, and memory is so cheap that devices actually have a reasonable amount of it instead of the absolute minimum.
Yeah, I'm sure that we could do that, and also with all the runtime module and all of that, I think we could do a lot of things. But yeah, for now we are still stuck with that. So that's what I wanted to do to say today.
Yeah, that looks like a fun board. I wonder if the PCIe slot, you said it has a slot on there, right? It's not like an edge connector, it's a slot. Yeah. So
no, it's
I
a
wonder
slot
if
like
that's I wonder if that's similar to the ZC102 where it's wired to the GTR sites on
I will tell you
the
that.
PS. Yeah.
I have to check on the documentation.
Right, yeah. So if it's like that, then I guess if you wanted to get PCIe out of there, probably that FMC would be the only way, I would think.
Yeah, maybe.
And I don't know if there's any, nice solutions for that. I mean, I know there's companies that if you buy it straight up, but is there something that's not exorbitantly expensive? This is something that we looked at a while ago. It's like, hey, could we get a PCIe to the big HTG 9200 boards? And while somebody did have a solution for that. I guess it was Samtech. They have a solution where there's an FMC that uses their little Firefly things, and then there's a PCIe card that also has little Firefly things. And that would work, but it's like, well, what if we want to put QSFPs on there? It would be nice if we had something else on the board that we could use for PCIe. They have a couple of Firefly ports on there, but it's a question of, could you adapt that to PCIe? So anyway, I guess that was an FMC Plus. So you can get 16 lanes of PCIe through the FMC Plus on there using that Samtech setup. But I think it's quite expensive, right? Because you need their proprietary FMC board, and you need the PCIe board, and you need the optical, Firefly modules to hook it all up. Yeah, so that's a bit of a tall order.
Yeah.
But it wouldn't surprise me if there's, other solutions that can do similar stuff. Oh, another thing to check, actually, now that I think about it, the ZC102 actually doesn't have any PCIe hard IP cores. So, the FPGA itself doesn't have any PCIe support. I mean, aside from the SoC, but we don't care about the SoC.
Yeah. Okay, but I have to check that.
That would be something to check on, because if it doesn't have any PCIe cores, then what's the point?
Yeah, absolutely.
Yeah. The ZC106, it does have PCIe cores. So, yeah. But I guess they probably wouldn't put a part.
I had in mind that when I look on this card, it was very similar to a 106. So I expect that it will be the case. We'll see.
Yeah. Definitely got to double check the schematic and the part number. I guess one good thing about Avnet, I think, is they have documentation available, schematics and such,
Yeah,
without having to jump through a
they
lot of
have
hoops.
everything.
Yeah,
Yeah.
no, it's like with High Tech
There is a
Global, you
site
got
with everything.
yeah. I was gonna say with companies like High Tech Global, they don't make anything available, and then even when you buy their board, then you got to go like twist their arm to send you a schematic. It took several back and forths to get schematics for these dang boards,
Yeah.
but what are you gonna do?
Yeah, on Avnet, it's a little bit rough to find it because they change URLs
Oh, right,
often.
yeah.
So
There's
but they redo the site and all of that, but it's okay. I
yeah.
mean, you
They seem to
I
like
got
rebuilding their site on every other year or
on
something.
exactly.
and break
So
all the external links. It's like like Xilinx did that with their
exactly.
forums for no apparent reason. I have not been on the Xilinx forums like since they did the redesign there. Do you know if it's still like active or if it's completely dead? I mean, they
I
just turned it
don't
into like a
remember. I
blog
mean,
comment section, so it's like yeah, it's terrible.
yeah, I agree. I don't remember
Yeah,
doing that as well. But
so sometimes you Google search and you find this link to Xilinx forum, which you know exactly what you asked for, but
Mm-hmm.
it's a dead end. It doesn't open.
Yep. Because they moved the page. Yeah. Yeah, it's like I used to browse the Xilinx forum occasionally. There were a couple of sub forums I would check and post occasionally and try to help people out. But with the new one, it's just like, ugh, it sucks. So I don't browse anymore. Yeah, they're really shooting themselves in the foot with that one. But it seems like, I don't know, AMD, they don't really care about people. They only care about companies.
not anymore. Yeah.
Yeah. What are you gonna do? And then Intel, I don't know what the situation is with Intel, right? I mean, they spun off their PSG group again as Altera again. But I don't know. I don't know what the status is of their forums and stuff. They gonna peel those off from the Intel ones again? We're gonna have the Altera forums back? I hope so. That would be nice. But who knows? Anyway, does anyone else have any questions or comments or going once, going twice? All right. Well, I guess we can adjourn for today then and talk to you guys in October, right? I think October 1st was going to be the next meeting, assuming everything works out with scheduling and stuff. We'll see if I have anything new to show you guys, because I'm going to be super busy with the research stuff here. So I don't know how much new stuff I'll be able to work on. But we'll see. I'm going to keep trying to chip away at stuff.
Okay,
Okay.
sounds good.
All right.
Bye bye.
Sounds good. Talk to you guys later.
See you.
See you.
Thanks.